Hi, my name is Stanley Samuel and I'm a PhD student at the Department of Computer Science and Automation, Indian Institute of Science in India. I'll be presenting our tool GenSys, which is a scalable fixed point engine for maximal controller synthesis or infinite state spaces. This is joint work with Professor Deepak D'Souza and Professor Raghavan Komandur. Automated synthesis of controllers, also known as reactive synthesis, is practically motivated and has applications in the domain of infinite state problems such as robot motion planning and wireless sensor networks. Due to the infinite nature of the state space, this problem is undecidable in general. In this talk, we will motivate our solution to this problem with an abstraction of the minimum backlog problem in wireless sensor networks, also known as the Cinderella-Stepmother game. Cinderella-Stepmother is a classic example of a game with infinite states and is considered a challenging problem for automated synthesis. The two players of the game are Cinderella, who is the protagonist player who we call the controller, and Stepmother, who is the environment or the adversary. The game has an infinite state space, which we denote by S, and consists of 5 buckets arranged in a circle with a fixed capacity of C units each. The allowable moves of each player are denoted by the transition predicates con SS prime and n SS prime respectively, where each player transitions the game state from S to S prime. These predicates are instantiated as follows. In each step, Cinderella is allowed to empty any two adjacent buckets, and then the stepmother tops up the buckets by arbitrarily partitioning one fresh unit of liquid across the 5 buckets. For this talk, we consider safety as a winning condition, and G of S as the predicate describing the set of safe states. For this game, G of S specifies that the buckets do not overflow, where C is the overflow limit as mentioned. A play of the game is an infinite sequence of steps where each step consists of a move by each player. Both players take turns in changing the state of the game and thus is a two-player alternating game. In this talk, we consider the controller or Cinderella as the first player. In this case, starting from state S, the controller plays first, followed by the environment, where state updates are denoted by primed variables. A play is winning for the controller, that is, does not reach an unsafe state, if each state in the play satisfies G of S. A game is winning for the controller, that is Cinderella in this case, from a state S, if it can ensure a winning play from S against any series of moves by the environment, who is a stepmother in this case. If the game is winning for the controller, the aim of synthesis is to find a winning region, that is WS, and a winning strategy for the controller. A winning region consists of a set of states from which the controller will win if it follows its strategy. The strategy tells the controller which move to play from any given state in the winning region. Cinderella has a winning strategy when C is greater than or equal to 2.0 and doesn't, that is, stepmother wins when C is between 0 and 2. The challenging range for automated synthesis has been conjectured to be between 1.5 and 2, but we show that GenSys can easily scale in this range when no other previous tool could. GenSys is a prototype tool written in Python and takes as input a game specification which essentially contains Python definitions describing the moves of the controller environment and the safe region as described in the previous example. These moves are in SMT-lib2 format. A condensed example of the Cinderella game specification for 3 buckets is shown. On running the specification for 5 buckets with the overflow limit as 3, we see that GenSys terminates with a clean readable strategy within milliseconds. On running it for the challenging range of 1 followed by 10 nines, we will see that GenSys terminates very fast within seconds and also gives the correct result. This shows that GenSys is very scalable. In this case, it terminated within 11 seconds. What GenSys essentially does is, based on this input specification, it formulates the game and employs a lean fixed point algorithm to compute the winning region and the strategy if it exists. It is possible that the procedure may not terminate, resulting in unknown. More details are explained in the accompanied paper. GenSys is guaranteed to synthesize a sound and maximal controller if it terminates. Soundness states that the controller can never lose starting from any state in the synthesized strategy. Maximality tells us that no state from where the controller can win upon initiation is missed. The results are promising and validate our claims of scalability as shown. In this talk, we have introduced GenSys as a scalable fixed point engine for the synthesis problem discussed. You can find our tool at the given link and more details in the paper.